Yeah, thanks Fabienne for kind introduction. And thanks Jeff and all for inviting me here. My pleasure to come here and give this presentation. And I think now it was time I select the next slide. So my talk will be on diagnosing hematologic neoplasms today and tomorrow. And this will be about sharing lots of thoughts about our work at MLL in the context of diagnosing hematologic neoplasms. So this is my disclosure statement. Essentially there's nothing to disclose. I'm not sure how long I would have to state this. I think it's okay for everyone. So I would like to make you aware of the content where I think hematologic diagnostics which is a cooperation of different methods. And we at some point built this slide here, which shows you, like, in proportion to the number of cases for a given time, for the different areas, like I for immunophenotyping, M for molecular, the combinations with other methods applying to single samples is being displayed. And except for molecular, who's oftentimes on their own, and this is BCR-ABL monitoring for CML patients, there's virtually no flow sample being not in combination with others. So that's the reality we are facing. And this is a total of the numbers of analysis we performed since MLL has been founded, since 2005. And of course, the majority, almost 900,000 samples have been analyzed by molecular, and about 500,000 by flow. And so that's obviously one of the focus of my talk, the management of the large amount of samples we are receiving. And this totals in almost 2.7 million analyses having been performed over these years. And you see here for the whole lab the numbers of samples having been analyzed. And this is very similar to what I learned today with your flow department, with steadily increasing numbers of cases being analyzed per year. So when we started the business in 2005, we thought that after 20 years we would be at 20,000, which would have been here. So it developed differently, and we had to face different aspects of lab management during this time to cope with these large numbers of samples. And we even have some ideas how to do this in the future, and that's the reason for the title of the talk. I would like to start with very simple things, which is order entry. And I think I learned American physicians are similar to German physicians that do not like exactly this software as compared to what is very convenient to them, which is somebody gives them a piece of paper and they just write something which should be the order, what they have to be, what they want to be analyzed. And so even here it's quite clearly written by an assistant and not by the physician. And but that's lots of paperwork. And we try to get rid of that and have introduced an order entry platform. Which is like within hospitals, you're used to have that, and you just digitally enter the analysis you want to have been done. And in fact, you can select here, and this is our product, the disease or the suspected disease, and then you get some suggestions what analyses are useful. But still, this is being used only for 10% of the samples because of the preference of many physicians to use paper still. And therefore, we are working on, and this is the first application of artificial intelligence, an AI approach to identify what they have written. And this, in fact, is working. More than 80% of cases, the complete handwriting can be extracted from the written form, and this for sure will increase in the future and will improve the procedures of our laboratory. And to end up, so this is the end then of the process. We will see everything in between of the samples is we provide digital reports the clients can download as PDF files. We not that much have integrated data transfer which directly is entered into the client's databases. And in fact, so I learned also Americans tend to still love fax transmission. I thought Germany was the last country extensively using that, but so yeah, you never know. People are used to that, and about half of them who have access to this digital report repository, they still want to have fax transmission in addition. I never understood why and never will, but yeah. Fax goes out from us automatically, so there's no single manual second spent to this process, but still it's part of a kind of strange process. We're going back to sample receipt now, and I will show something which is in the process of being established, which is a composition of automated hematology analysis, which is a system by Sysmex, which includes full blood count, like every clinical chemistry lab does, but this will also automatically prepare smears and do digital images, which then, based on AI algorithms, will be classified. And it includes an aliquoting system we will see here, which needs to be fed with homogeneously prepared tubes. And what we get, and you will experience the same, is a large variety of different primary tubes. And so for this, we will build an Hamilton pipetting device. And all of this will be connected by a Roche transportation system. So this is a three-dimensional sketch of what we're planning. And so these are about one such area, 500 square meters. And Jeff, what did we say? How many square? 5,000 square feet, okay. Thanks. And so 2/3 of that will be used for such system. And you can see here a floor plan of that. And most importantly, so I'm not used to what you do. So my office is this one, and I will sit directly next to that one. And here to the left will be the flow department. And so we're constructing this. And one such device, as you see here, is the stage like it was this morning. So it's being constructed. There's no Roche system attached to that, but we are planning to put this into service by the end of this year. Focusing then on flow cytometry, you see here the numbers of cases for the last 12 years. Separated according to the different panels we are applying. Of course, the most frequent one, CLL or B-cell lymphoma panel, and then here the others. And you see for everything an increase in the numbers of samples being analyzed. And that makes clear that we will benefit from automation of any parts of the sample processing, and that's what we are aiming for. And first step there, in automizing the flow lab is the sample receipt in the flow department, and you do not need to read everything which is there, which by the way is in German language, but you see here there's the antibody panels put into our database, and this information is then stored in the database and transferred to a server, where our pipetting device can grab this information. And this is just a photo of this device, which is quite large. It's three different platforms. Here you see one, here's the second, and on behind there's an additional one. And then there's a hotel which is managing all the plates which we are operating. And the principles is that we put in the sample tubes here, and we get out the plates with the samples being prepared ready for the cytometer here. And in between, samples will be centrifuged on the platform, as you see here. And here are the antibodies. We will see this in more detail in a second. And you can see here, so it's a total of 4 platforms, and we have connected them with each other by this transportation arm. As you see here, this one is just transferring one plate from one place to the other, and then the respective device will keep taking care of that particular plate. So this is the store which is now grabbing this plate and putting it back into the store. We have taken advantage in the past of antibodies being not anymore provided in liquid solution, because that was something which made it difficult to really automate sample preparation. We had prior systems of automation, and if you have the liquid solution of the antibody and take off the cap, then it's connected to oxygen and is drying, and this is not good for the fluorochromes, of course. And therefore we were happy that these duraclones were introduced, where the antibodies are provided in dry format. And in fact, we have had this for all of our panels, which are all 10 color combinations. So just one final cocktail per sample in one tube. But of course, that was not a solution being applicable to an automated pipetting device. And therefore, we asked Beckman Coulter to provide this in 96 well plates. And you see here the storage system, which handles all the plates. And here again, what we've seen before, the area where these plates are being placed. And this pipetting device is then using the information we've seen before in our LIMS system, where the panels per patient are being entered, and according to this information, will pipette the respective antibodies and bring them together with the samples, which are then in 48 well plates transferred into the Cytoflex cytometers. And no data is entered twice. All data which once has been entered will be transferred and connected via barcodes, which are read when before we place the respective plate into the cytometer here, and then this cytometer exactly knows which 48 samples are being analyzed. And another step then of automation in the flow department is the one we see here, which is applying a higher number of samples, a higher number of colors, which will reduce the number of tubes we will have to use per particular sample and panel or set of antigens we want to analyze. And this was just a sketch with the 2 pipetting devices we have. We just recently acquired the third one to increase the daily capacity from 280 to 420, which we need today. And so that was the sketch. We were able to make different runs, like you see here, the blue bars for one machine and the orange bars for the other machine. And if we increase the numbers of conjugates from 10 to 13 or 18, you for sure see there's an increase of capacity using the same pipetting devices regarding to the use of 10 color combinations. And here's just a sketch, which is still not finalized, but of the antibody combinations applying 16 colors, where we in fact, so the largest advancement will be for the B-cell lymphoma cases, where we reduce our panel from 3 tubes to 1 tube. So it will be only a third of the pipetting we will need. And another significant improvement is for the myeloid neoplasms, where we have for surface staining 3-tube AML panel and a 3-tube MDS panel. And oftentimes we are not, so we're not using a screening tube. We just make our best guess what the appropriate panel will be, and then select this one. And in 10% of cases, we have to do reflex testing. In particular, in AML, sometimes we have to add an MDS tube and vice versa. And out of these 3 and 3 tubes, we just make 2 tubes, which will fit anyway, because everything is being analyzed then by these 2 tubes. And we anticipate a significant improvement of sample processing by this approach. And I would like to turn then to the areas of application of artificial intelligence. Still an example of flow cytometry. We also will see this in other areas in a minute, in other diagnostic areas. So this is the conventional display of analysis we're performing, and we try to perform dimensionality reduction, which is shown here in a kind of a Tisney plot, and which ideally will result in identification of an abnormal and a target population. And we are working on 2 areas. One is to improve the algorithms which predict the disease outcome. And here, or most important, because of affecting the largest number of cases, the most important algorithm is identifying and separating no-lymphoma cases from lymphoma cases. And you can see here that the accuracy already is very high. So from the point of view of the algorithm, we are ready to use this in daily routine. Question still is different from like morphology, where you can double check based on the digital picture if the algorithm identified correctly the cell type. There's no such picture in flow. So you have to gate and do the analysis and see the dot plots. And of course, we want to get rid of this work, and we will see examples for this in a minute. We also will try to separate the positive cases from each other. This is an area we are still working on because we think accuracy of less than 90% is not appropriate, but this is still in progress. You can see here then the readout of the artificial intelligence derived information, which is directly linked to our LIMS system. And we have added this for prospective testing of the artificially generated dot plots. So you will see the prediction here with the prediction probability. So in this case, there's a high probability of CLL, and you see color-coded the population of interest, and you can double-check if the displayed phenotype in fact matches the predicted class. And what we are validating at the moment is the quality of these artificially generated dot plots, because these are the ones which will allow us in future to still bring in our expertise and confirm that the prediction is correct. So I would like to touch then other areas of the laboratory and procedures and applications of artificial intelligence there, and start with cytomorphology. And so it has been an area of trying to improve by counting more cells. And I'm not sure you're aware of this Rühmke paper, which just applied statistics, as you can see here. So there's argues about which number of cells should be evaluated when making a differential in peripheral blood or also in bone marrow aspirate. And you can see here, this is just the true percentage, and if you just added 95% confidence interval to that, you see that for 8%, counting 100 events, the confidence interval is 3% to 16%. And if you count 200, what many do, it just decreases slightly the range from 4 to 13%, and you would have to count 1,000 cells to get to a maybe acceptable degree of variation. So that's not necessarily useful in improving the accuracy of what we do. It might be using artificial intelligence, and we have implemented here a system we have kind of stolen for cytogenetics. We use this in cytogenetics since decades, and this automatically takes pictures of the respective cells. Here an example of peripheral blood, and these cells are then classified. You see here the magnified pictures at higher resolution, and we prospectively tested this in almost 30,000 patients and compared 3 million cells manually differentiated to 14 million cells automatically differentiated, and we found overall a confidence of 95% regarding malignant or critical cells, which is similar to what humans do. And we are applying this now in our routine, and cases are being processed with this procedure, are automatically analyzed, and you get an automatically generated differential, which you will have to double check, and then this already saves us a significant amount of workforce time. We see here the performance of the AI-derived cell classification with the expert-derived cell classification, which is at 95%, 94%, and this is clearly better than the interhuman classification accuracy is being considered to be. We have now integrated this in our routine workflow and implement this, including upload of the pictures and then doing our routine workflow with double checking of the pictures and then deriving the report from that. And so this is now part of our procedures and integrated into routine. What we have not integrated into routine is bone marrow evaluation, where we face the challenge of identifying cells. And so we are using algorithms aiming at identifying structures which correlate to single cells, and are approaching then to apply or develop AI algorithms to these pictures also, like we did for peripheral blood, to derive an automated classification also for bone marrow, which of course will be more complex than peripheral blood because of the different, the higher number of the different stages of normal cells and the need for separating them from abnormal cells. Covering then cytogenetics, this gives you an idea of the workflow. So we will have to select at least 20 metafaces, do manual work of editing the digital pictures again, and then do the karyotyping, and then analyze the karyograms and get the final readout, which results in a normal karyotype. On the way to that, we have different machines which automate all different aspects of the single steps of the procedures when preparing the chromosome analysis. And this will be automatically captured then in the system we've seen for cytomorphology. We have similar automates for fish analysis, and you see here the bunch of fish probes which are being automatically pipetted and prepared in a way to be analyzed. And I think, well, do we see the video? Here we see the video, and this just reflects how we process the samples. So in that frame we put 5 slides. Everything is barcoded, the slides as well as the frame, and then after an overview scan has been done with a lower magnification, the system will recognize where the chromosomes are located, and then we will do a higher magnification picture after having put oil also automatically on the slides. And then these pictures can be digitally processed. And this has been the step where the technicians jumped in, and they had to, like you see here, I just started the video, identified the single chromosomes and then separated them from each other by drawing lines between them and cutted them. So you see this is a quite manual step and takes some time. And so I would cut this short. They will be working, and this is a highly skilled technician who did this like 45 seconds on one case before it's finished. And you see now what we, together with Meta Systems, developed as an AI-based automated readout. I will start the video now. And then after a few seconds, we are done. And by the way, the time it takes does not even matter as compared to the getting rid of all the technicians' time needed to process these samples. So all of our samples are processed this way now, which gave us a great deal of automation and improvement of efficiency of our work. Coming then to molecular, just some ideas of how we automated there. So we have, in fact, 4 of these systems which are used to aliquot the samples for storage. We will save aliquots of 5 million cells, which are then ready to DNA extraction or RNA extraction. They're placed into barcoded tubes. You see here the tubes from the bottom with 2D barcodes. So we have no labeling, no more any tubes in these paper boxes with 100 spots where you can take out manually the samples you're looking for. It's all automated, and they are stored in these devices here, and we will see some details on that right now. Here's so you have to pipette, and then you have to make sure what you put in there will be kept there. So you have to cap. This is an automated capping device you see here, and there's a process of capping 96 tubes in parallel. And this is a plate with only a few tubes in there, and each step before we process anywhere in the molecular lab, we apply barcode scanning, so we exactly know before each step at which position the respective tube is located. And so it wouldn't even harm our procedures if such a plate would fall down and would be messed up regarding the order it had before, because everything is identified via the barcode, and all analysis devices will be provided with this information. And you've seen in the dark now the storage area where the samples are being stored at -80 degree and at -20 degree, and then plates are placed into this device, as you see here, and then this system automatically will take one tube at a time from one plate to the other, which looks like being rather slow. It is, but again, most importantly, it works without any manual input. And when we want to get our samples ready in the morning for being placed into an analysis system, we get them out of these systems without having manually selected any of these cases. And they go then for analysis on the sequencers. So we just recently, a few months ago, acquired these two, which are the new NovaSeq, the NovaSeq X Plus, which have, in comparison to the ones we used before, NovaSeq 6000, have higher capacity. So we had 5 of these NovaSeq 6000, which are now being replaced by the 2 only machines of the NovaSeq X Plus. And we are running large panels, as you do here. This is the myeloid panel. And regarding data interpretation of NGS, there are different steps. There's data pre-processing, then there's variant discovery, and most importantly, then the variant interpretation. And we access different databases, and most importantly, the MLL predictor, which has been generated by ourselves, taken advantage of the different databases, but most importantly of our database, or our experience with particular mutations where we know this one is disease-related and the other one will not be disease-related, but just a SNP. This is being automatically provided, this information, and helps the scientist to interpret the variants and to provide then the respective report. We have performed our so-called 5,000 genomes project to prove if there's a way from panel sequencing to genomes. And this is just to clarify the amount of sequencing we will have to do. So you see here a small dot. You may not have recognized this. This is in relation to what we've seen, what we will see, the amount of target sequencing. If we compare this to whole exome sequencing, it's much more, and this is whole genome sequencing. So there's a need to handle large amounts of data, which we store in the cloud and also process in the cloud. And we have set up a workflow which will allow us, with a turnaround time of between 5 and 7 days, to process samples for whole genome sequencing. There's no routine clinical application so far for whole genome sequencing, but in fact, so we ran a program for difficult cases which have been analyzed by whatever, and no disease could be identified. And we found in a third of these cases that whole genome sequencing in fact identified mutations which then were interpreted as being related to the symptoms the patient had. So far we analyzed in the project almost 5,000 genomes, and together with additional samples being processed in other research projects, more than 6,000 genomes now. And what we will get out of that is a combination of the readout, which you see here, which we don't go into detail, regarding mutations and also structural abnormalities. And you see here data derived from whole transcriptome sequencing, which is then translocations, and you can clearly see that the pictures we see for different disease groups clearly differ from each other. And we've performed an analysis combining or using only single parts of these analyses, or combined all readouts which can be derived from the combination of whole genome and whole transcriptome sequencing. And we found out that using this data in an isolated way without any further diagnostic methods, the accuracy with standard diagnostics was almost 90%. And as an example, this is even capable of separating AML from MDS, which is cut by a 20% blast count, but which we know have different patterns of molecular mutations as a basis, and for sure these combinations will be capable of identifying these. And for whole transcriptome sequencing, we already used this in routine workup of B-cell precursor ALLs to identify cases like this with a DAX4 mutation. We also use artificial intelligence after we have finished the analytical part of diagnostics by applying large language models, which is shown here. So we've been trying this in cytomorphology, using data derived by morphology and also other methods, which were then compared to similar cases provided from our repository. And we tried to derive the report out of that. And besides some more formal aspects being automatically processed, we found that we have an overall of 88% accuracy of these reports. An example is here, and so you don't have to read all the words one after the other. I did, and many did, and you cannot tell the difference which one has been prepared by the large language model and which one is being prepared by a human. So it's not 100%. Reaching 100% always is difficult if you compare to data provided by humans, but I think it's on its way, and it will be the future of providing reports. So the upper one was the artificially created one, and the lower one was the human created one. And this will all be put into the integrated report, which we provide also today, but with lots of manual working, which will summarize the data from the respective diagnostic departments and give an integrated interpretation of the whole case and also some recommendations. And there also we have to be aware of that, for instance, considering clinical trials, no one will have all these in mind and will be capable of suggesting appropriate clinical trials. And there are lots of resources to be used and considered when trying to make the most out of the reports we generate. And so our plan is to also implement these resources into an AI-based approach to really consider all this information then and provide this in a summarized report. And we made a calculation of the effect of using audio or video material, and in addition which was automatically processed by this AI approach, which lasted for 2 minutes only, and then another half a minute to prepare the report as a summary. And when we compare this to a human process, this would correlate to a total of 45 minutes, which clearly demonstrates, so that's not ready for use, but this is a first approach, and demonstrates the potential of application of AI also in this area. And with this, I would like to conclude, and thank you for listening, and I'm looking forward to taking any questions. And I was asked to show this slide because you will need this for your CME, I think. Thanks for listening.
I have a question. That was a great talk. I'm not a hematopathologist, but one question that occurs to me is, can you comment a little bit on the regulatory environment in Germany in terms of implementation of these AI-based algorithms, and whether that's regulated in some way in the context of medical diagnostics?
Yeah, so I've been asked to repeat the question. That was in general to what's the degree of regulation in the EU by applying artificial intelligence. There are increasing amounts of regulations on that, and some of them are from the EU, some of them are from national authorities. And so we do not clearly see where we get with that. But what we can state for this time is, as long as the final data interpretation is being done by a human expert, and the sign-off of the report, then we are okay. But we are moving into directions. So I've shown that for the flow data, for the artificially generated dot plots, and we are relying then in part on these products, and there are regulations on that, and but so far overall I would state that it's feasible to cope with that and to put this into practice anyway. And the regulations are needed, of course, because this is a significant potential source of error if it's not done adequately. So I'm clearly in favor of such regulations. Yeah.
Thank you, Wolfgang. That was outstanding. You had one slide that you showed where an accuracy of an AI was somewhat better than a human expert. It must be the case that in some of these where you've compared them, even if they have similar accuracies, that humans find some AI mistakes, but AI might probably find some human mistakes. At some point, in some contexts, maybe the AI is going to routinely be better than humans. At what point do we stop using humans in these analyses? Are there some where you think that it's ready right now, or is there something where you think we'll never be able to trust an AI to take some of these classification tasks?
So I would clearly say we should stop before aiming at 100%, because we never will get there. And then it depends on what you're dealing with. I think we have to differentiate prediction of a disease from like predicting cell types when preparing a differential, because the consequences are less if the differential goes into this or the next category as compared if there's a malignant disease and it's not identified. And I think we have to be safe in identifying or excluding malignancies, And there we should be at almost 100%. But in the other areas, as long as the expert will recognize, then we can take advantage of the AI-based systems, even if they have only like 90% accuracy. They're not necessarily used to do the work better than the humans, but to get rid of manual work. Anyway, we will have to face that humans do mistakes. And there are some statistics, I'm not familiar with how valid they are, in each area of laboratory medicine, of degrees of wrong, or at least partly wrong reports, and they are clearly higher than 1%. They are like in the area of between 1 and 10%, depending on what you consider wrong and non-exact. And I think we will have to figure out the answer to your question, which is absolutely relevant in this area. But I think we will strongly have to try to use AI-derived products to help us in our routine diagnostics every day, and not aiming for 100%, but see if it's a reasonable approach, which then again will be matching the regulatory provisions. This please.
Really elegant automation work. Thank you for sharing that with us. I was curious, how have you changed your staffing models as you've brought on a variety of sort of efficiencies?
Yeah, so question was on change of staffing models during the course of increasing amount of automation. And we most clearly saw this with the technicians. So in fact, when we introduced the first systems for automated pipetting, there was a significant number of technicians being against, because they said, I learned this in school and I want to apply pipetting. And it's okay, but the proportion of such technicians continuously decreased over the years. And so we now select, in fact, our stuff, and that's not only true for technicians, also for scientists, for those who are open to innovation and open to changes. And I think that had a significant impact on how we acquire personnel.
It sounds like you continue to hire. So does that mean that your staff is able to do other things, or has there been sort of a contraction and re-expansion?
Yeah. So the amount of workforce directly involved in diagnostics is not increasing to the same degree as the sample workload. We still hire, and we are a small medium enterprise, right? When we began, we were 29 people, and we were 4 founders, and they did everything else the employees did not do. So we're working all day, and we thought we could do everything. But at some point you recognize you can't, and you will have to implement structures like HR department and accounting department and what else. And so we still hire people, and we still hire people working in diagnostics, but to a lower degree as compared to the increase of sample volume. And they do more the intellectual work than the manual work, that's for sure.
I would just add to that question, are you employing some of these automation or AI tools to the more mundane non-medical work? So your policies and procedures, your billing, your workflow, your hiring, your HR, are you applying AI and machine learning and language tools to those areas?
So a question was application of AI tools to the non-diagnostic areas. Answer is not yet, but we're on the way through this. We're figuring out, again, regarding regulations, because it's not that easy reading out applications, because it's personal data, and the algorithms you can apply uses all the data you feed into the system. So you would have to have isolated systems which do not provide any information outside your company. But we're working on that. Also for accounting, we have a plan already how to identify cases which are very much similar to prior cases where there's virtually no intellectual input when preparing the invoice, and this will be completely automized. We recently implemented an ERP system which allows us to automatically assign the invoices we get to the order we placed, and even to prepare an automated payment. So there are lots of areas where we use this, and I think, like in real life outside the laboratory, AI-derived products will be a significant part of our life. Yes, please.
Does MLL use any kind of formal mechanisms for promoting innovation? Like I'm thinking of like Six Sigma or other sort of kind of formal quality management and idea management systems?
Yeah, question was on like formal procedures, and so if we use that, I'm not too familiar with that, and you can imagine the answer is rather no. It largely, in fact, relies on personal expertise, in particular from the AI guys. So we've done lots of work in cooperation with Amazon Web Services, and but we wanted to improve on that and have a more continuous basis for our personnel. So it was just 2 years ago that we hired then the best person from AWS, who's now the head of our team, and he acquired a total of 8 people now dealing with AI. And for sure, we will have to implement such processes. We use AI, and we try to use AI for coding. So our informatics guys will ask automated tools applying AI to text the code, and we already have seen the decrease in the workload by a third of the time they had to spend. Who wants first? Yeah.
Okay, so I'm going to ask like a more specific question. So I know the accuracy is very high, but when you analyze the AI analyze the flow cytometry data, if it gets wrong, so then do you have to get like a reanalyzing the kind of like conventional software, or like does these two provide like a platform to analyze on the cloud?
Yeah, the question was what to do with the cases considered inaccurate if we have to go into detail. We have no solution for that. So when we figure out it's too complicated, we go back to the FCS files and the Calusa software and do the conventional analysis. And in fact, the AI tool will put out cases where it indicates here the prediction probability is very low. Don't use the result of AI, and then we will have to use the manual process again. So for the time being, this will be a significant part still of our work. Yes.
That was a great talk, Wolfgang. Thanks for giving a question about the distribution of your cases. How many are diagnostic and how many are follow-up? And does that make a difference for this type of tool? Also, can you incorporate into the model things like the type of therapy the patients received? Is that something that can be included?
Yeah. So question was in relation to diagnostic and follow-up samples and to integrating information on therapy, and I think you meant also prior findings of the same patient. We're working on that. This is just for diagnostic cases now. For lymphoma, it's easier to also being applied for follow-up cases. Regarding type of therapy, that's not exactly a strength of our setting, because we have to manually collect all such data. I think we're quite far away of considering this, but next topic will be application in MRD analysis, which will be a challenge with my favorite disease, which is AML, because of course of the heterogeneity, and but we definitely will go that way. Yes.
You have specific sample types that you keep manual to start with, or that you only do manual analysis to start with, like CSF or like problem sample types?
Yes, these are the one with special materials or fluids. We just use the pipetting device for peripheral blood and bone marrow aspirates, and for any fluids with a high cell count. The others, and CSF in particular, we always do manually. So that's a rule I had to learn. You can automate a lot, and if you have automated 90% of the process and you want to automate the remaining 10%, it will be the same effort again. So nobody does, in fact. And yeah, and there will also be like low quality bone marrow aspirates where we do manual processing still.
Are the reagents for your dry down tube all from the same vendor, or do you have combined reagents?
We have combined reagents. Of course, majority is from the same vendor, but they are in general open to implementing also products from other vendors. But there are sometimes, I at least know one German company who do not allow to implement this, and yeah, that's a bit of a challenge. But so we're interested in solutions, and there are differences in the different conjugates, of course. But we try as long as we need to get adequate results, and this is okay even with the majority from one vendor. Thank you.